Okay. Have a Jupyter notebook open somewhere. Here it is. Okay. Okay, is the text in this Jupyter notebook big? You know what? This is easy to fix. Let me just zoom a few times. Okay, so what I want to show is a very convenient way of distributing code over the over the cluster. Some of what I'm going to show will also work on a local machine. Like if you have, you know, a couple of CPUs with a couple of cores each, you can parallelize in that environment too, using what I'm going to show. But mostly what I'm showing is about distributing things on the Janelia compute cluster with just a few extra lines. And I promise I had this here before you showed up in the meeting, Boaz, but I want to credit this fine gentleman for submitting a pull request to one of my repositories with the core idea of what I think is cool about this. And I'll point that out, especially when I get to that spot. This notebook will also be on the wiki for the how-to interest group page. So if you want to look at this or run it yourself, then you'll be able to. And so at the top are a couple of links to some of the resources for background material here. I'm going to be using DASK, which stands for Distributed Task Scheduler. It's a way of distributing code over multiple compute resources and planning long computations before you execute them so that the distributed environment can determine an optimal way of executing the work. I'm going to use DASK arrays, which does everything I just mentioned on DASK, but specifically on like ND array type data. And I'm going to be using a repository that I wrote called Cluster Wrap that's supposed to simplify a lot of the boilerplate things for doing DASK computing at Janelia. Okay, so first I'll refresh this environment so that you know I'm in a totally clean environment and no variables are already defined. And first I'm just going to get a directory that contains a bunch of image files as HDF5 files. So this is what's in the directory. A bunch of I think it's 21 images. They're just time points from a 4D imaging experiment. And what I want to do is take the mean of all 21 of these images over the time axis. So I want to end up with a single 3D image that is, you know, the voxel-wise mean of all of these 21 images. You could just do this in a for loop, load image, add it to an accumulator, load the next image, add it to an accumulator, and then at the end, divide by the total number of images that you loaded. That would take a little while. And as the number of images you have increases, the amount of time required would increase too. So even for these 21 images, that would probably take like 25, 30 minutes. So what I'm going to show you will finish a lot faster than that. So we've got this directory located on disk with all of these 21 images in it. The next thing I'm going to do is wrap those images up into a DASK array object. So there's 3 lines of code in here. First, I'm importing a function that's going to do this for me. It's called DASK array backed by HDF5. And it's going to take the directory that contains these images, a prefix, something at the beginning of all the image paths, a suffix, something at the end of all the image paths. And then because these are HDF5 files, that means that there could be multiple data sets inside each file. This dataset path uniquely identifies the specific image within the HDF5 file that I want. And this function is going to return an object that sort of summarizes all of these images on disk. So I'm printing out what this thing is, all images DASK array. It is a DASK array. This is the shape of this 4-dimensional array. The axes are time, z, y, x. The data type is an unsigned 16-bit integer, and this chunk size is something unique to DASK arrays. If you've only worked with NumPy and not DASK, it's telling, or you know, it's recording of all of the data in this array. If I were to distribute it in parallel on some computing, you know, parallel computing system, what are the units of parallelization to be sent to each worker? And so what I've specified, I want each 3D image, each complete 3D image for each time point to be a separate chunk. So I want each full 3D image to be handled separately. Running this did not actually load any of these 21 images into memory. Each one of these images is probably a gigabyte uncompressed, maybe, I don't know, 3/4 or 1 1/4 gigabytes, something like that. So it would have taken a lot longer to load this, say, 30 gigabytes into RAM, but this returned pretty quickly. So what's actually happened here when I ran this function is that this variable doesn't contain the actual raw data of these images. It contains the plans for how to load each chunk at the time in which you finally tell DASK to execute your code. Okay, so this is where the interesting stuff actually starts to happen. The next thing I want to do is define my function for taking the mean over these images, and I want that function to use a cluster. So I'm importing this decorator, this function decorator, from my own repository called cluster wrap. But this is where Boaz's contribution came. He's the one who showed me how to use a decorator to do this specific thing. So I'm defining a function here called distributed mean over a DASK array, but I'm tagging the beginning of that cluster with this, or the beginning of that function with this decorator called cluster. This is going to wrap this whole function in something that will create a cluster if one is needed, and then when the function is complete, shut that cluster back down for you. And so you don't have to do any of that work for setting the cluster up. You just have to put @cluster at the beginning of your function definition to ensure that it will run in the cluster environment. So this function is going to take the DASK array as input, and then these two arguments are required. Cluster, the default value will be none, and then cluster keyword arguments, which is going to help you determine at function execution time how you want your cluster to be designed. How many workers do you want? How many CPU cores should each worker be made out of? How many threads should each CPU or each worker be allowed to run in parallel? And then the actual computing in here is very simple. I simply take the mean over this DASK array over the first axis, which was our time axis. And then this dot compute says, don't just plan to do this computation later, DASK array. I want you to actually execute it. You're now in an environment where a cluster exists, so you have the resources to do this computation. So running this will be like instantaneous because all we're doing is defining things. Now we want to actually run the function. So here I'm actually calling the function distributed mean DASK array, and my output is going to be stored in this variable image mean. And I'm giving it as the first argument, all images DASK array. That's what we defined up here, all images DASK array, this lazy representation of all the data that's on disk. And then this other argument, cluster keyword arguments. Like I said, this is how you tell the cluster that you're going to build in DASK what it should be made out of. In scientific computing, we have to bill everything we run on the cluster to a specific project. If you're in a research lab, you probably don't need this line because it will be by default, all of your cluster resources will be billed to your lab. But then, like I said, each worker will be made out of, in my case, 2 CPUs and only be allowed to run 1 thread. And I'm saying the minimum number of workers you're allowed to have cluster is 10 and the max is 10. So I just want a cluster that has exactly 10 workers, but you can have these numbers be different, and the cluster will auto scale how many workers it has based on the amount of work you give it to do. It'll start with some reasonably small number, and then if it decides, hey, this is taking too long, it'll start adding more workers to further parallelize your job. So let me execute this cell. And the first thing that happens is this link pops up, which is a link to the DASK dashboard, which is going to show us what the DASK cluster is doing in real time as it executes your compute job. So if I click on workers, it should show me that there are 10 workers, and now they've all actually gotten started already, and their CPU load should be close to around 100% for the duration of the entire job, because I only allowed 1 thread to run for each worker. So it's saying I'm using 100% of the only thread that you let me run. There's other cool stuff in this DASK dashboard. So like graph, for example, will show me the computation that I'm executing on the cluster. Each one of these nodes represents an individual task. So this is like loading the 21 images off of disk and into memory separately on each worker. This should be like combining pieces, the chunks of those images together on a worker, and then those workers are then sharing each of their results together in aggregates, mean, combined, partial, and then again aggregating, and then finally giving you your final result. And then this is the default page, the status page, which shows you, some of the same information you saw on graph, but it's showing it actually as it's being executed on the cluster. So this will take another 30 or 40 seconds probably. It looks like there's only 1 worker left. It's probably the last one that's aggregating all of the pieces of that mean computation. And we'll wait for it to finish, because what I want to show is that when this cell completes, the cluster will automatically be shut down for you. All of the workers that were allocated to run this job on the compute cluster will be automatically closed, which just happened. So the cell is complete. There's some, I think bugs in this, probably not bugs, but this underlying library called Tornado that DASK is based on always gives me a really nasty looking output when clusters shut down. But that does not affect the validity of the computation I just ran. So this image mean object, what is it? I'm printing out, first of all, what type of object it is. And then I happen to know it's a NumPy array. So I want to see what the shape of the NumPy array is. So that's all down here under these ugly warning outputs. But in this case, the object that we received from the output of our computation is a NumPy array, not a DASK array. So what that means is that it's no longer a lazy object. I actually have in memory the single 3D image, which is the mean over all the time points of the images that I loaded. Okay, so just review really quick there. I was able to construct a cluster of with a custom number of workers, each composed of a custom number of CPUs and threads for my function simply by tagging it with this decorator at the beginning. And that handles everything about setting up and tearing the cluster down before and after your function executes. But what happens if you already have a cluster defined? Maybe you want your cluster to last longer than just the duration of the single function that you're running. So you can construct a static cluster that will live as long as you want it to live. I can say, from cluster app import cluster, and then just build my own cluster here that I call static cluster. And notice I'm giving it the same arguments as before. I guess I'm accidentally giving it 2 threads instead of 1, but it doesn't make a difference. So if I run this, I get the DASK dashboard link again. Let me close the older one. And what I want to show for this DASK dashboard is that in a minute, these workers will actually get allocated. Construction of the cluster propagates, it communicates with LSF, which then constructs each worker as an individual B sub job. And now these workers are just sitting here waiting for something to do. I've got the workers ready, but the CPU load on all of them is between 0 and 4% because they're just sitting there idle. All they're doing is sort of communicating with each other, saying, hey, we're ready. Do you have any work to do? Hey, scheduler, do you have any work for us to do? And so this is a static cluster just waiting for me to execute something. And now I'm going to execute the same function here. But notice the cluster keywords argument is gone because we've already specified how the cluster is going to be built. Instead, we're going to provide a cluster object through the cluster keyword argument. We're saying we've already got a cluster, so you don't need to make one yourself. Just run this code on the existing cluster. So now the workers are all busy. Their CPU load has all gone up to, close to 100%, something like that. And we'll see in the status window, these jobs are, this is all the data getting loaded off disk in parallel by each worker into memory locally on each worker. And then after a while, you'll start seeing these mean combined partials complete, which is like sending data between workers, adding it all together and computing your image mean. And then, so this will finish, and image mean here will be exactly the same as image mean here was. The only difference is that in this instance, the cluster only lived as long as the function did. And in this instance, we made the cluster in advance because we might want to use it for something else later. And then you can run an arbitrary number of functions using that cluster. And then you would have to manually close the cluster later. You manually built it, you got to manually close it. Otherwise, it'll just live as long as LSF will allow it to live, and then finally close it itself and then bill you. So what'll happen is that when this finishes running, I will run this, and that will manually close the cluster that I manually constructed. Okay, that was everything I wanted to show. Any questions?
I have a question.
Sure.
So, this is the client side, so this is the user side. From the cluster side, what do you need to be installed as a job manager or something?
Nothing in this case. So I'm communicating with the Janelia cluster, which I happen to know is LSF. And so this cluster wrap Python module is aware of that in advance. So notice when I first ran this up here, I imported this circuit seeker module that also imports cluster wrap. And when cluster wrap got imported, it checked to see if bsub was in the environment. And when that's what this is. This is the output of checking if bsub is in the environment. So this is saying like, oh, sure, IBM Spectrum LSF is here. So knowing that, cluster wrap says, okay, when I actually construct a cluster, what I need to do is submit a B sub job for each worker. And he's going to tell me how, or the code is going to tell me how many CPUs each B sub job needs, and so on and so forth. So if you wanted to run this on a different cluster that used, say, Slurm or SGE, then that would need to be added to cluster wrap as another cluster manager that needs to be communicated with. And there are existing tools in the DASK community, a library called DASK job queue, that makes that pretty seamless. It would basically be copying my existing code for the LSF cluster, changing a few lines to say, hey, this is SGE or Slurm instead, and then it would work in those environments too.
Thank you.
Yeah. Conrad?
Yeah, so thanks, Greg. That was cool. I just I'm struggling to understand how the parallelization is done, because it seems like your mean is across the time points, right? But your unit of parallelization is an image. So then, you know, like I would expect
it's hidden in this mean function. So this is a nice thing about DASK array, is that it's got a bunch of built-in, like almost everything that can be done on NumPy arrays can also be done on DASK arrays. So when I'm calling mean here, it's the DASK array method, not the NumPy method. And the DASK array method knows that, okay, I'm taking a mean over this axis, and I know that this is the unit of parallelization that the user has chosen, like these chunks. And it goes, okay, but what I actually have to do is combine things over this axis. So first, it's just going to load each worker is going to say, okay, I need to load one chunk at a time, things off disk. Worker A gets the first two chunks. Worker B gets the next two chunks. They get distributed, you know, in a sort of a round robin fashion over overall workers. And then it goes, oh, I'm running the mean function. What that means is I need to add over this axis. And the scheduler will determine, okay, worker A has 2 chunks. I'll add these locally. Worker B has 4 chunks. I'll add all those locally. So it's just doing this sum in a sort of chunk-wise manner. And then as soon as it realizes, oh, worker A has the sum over the first 3 images, worker B has the sum over the next 4 images, then it goes, okay, now I can't do any more local adding. Now I'm going to add between workers, and it'll send that cumulative sum from worker A to worker B, and then add those. And iteratively, you'll end up with a final sum happening on just one worker, which is the sum over all images for that axis.
Okay, I see. So it's not loading. So worker 1 isn't loading entire image A. It's loading a chunk of image A and a chunk of image B, and taking the mean.
No, in this case, it is loading. Worker A should be loading like 2 images probably, and then worker B is loading 2 images, and then worker C is loading 2 images, and then each of those workers adds their 2 images, and then as soon as no more local addition can happen within a worker, the scheduler figures out, oh, okay, now I need to send one of the partial results from a worker to a different worker. And then now you have 2 things on that worker, those get added. And so it happens in sort of a logarithmic way, like the total number of cross-worker communication.
Yeah, okay, so that makes sense. But then how would this scale if your image was really big, right?
You could change the chunk size. So here I manually specified that this is hidden in this DASK array backed by HDF5 function, that I want my chunk size to be 1 time point, but the whole 3D image. But there's a keyword here that you can optionally use to provide the chunk size manually. And then you could say, well, actually what I want is 1 time point, but only half of X or something. So it's totally arbitrary how you choose to chunk the image. And the DASK scheduler will do all of the figuring out for you of like how things need to be loaded in each worker, how they need to be shared between workers. But you can configure it in ways that are really good, that work well with the scheduler. You can also configure it in ways that are really bad, where like if your choice for how you chunk things and how you're reading them off disk is like really poor, DASK could end up being slower than just the serial solution because you sort of haven't set it up for success. So there is a little bit of most of the time the like right way to do it is pretty obvious, but I always still tend to screw it up once or twice before I figure it out.
Also, what's nice about DASK, sorry, is that with your DASK status, there's also performance. So you can see which function spent how much time, and you can see how much time was for communication. So if you go to profile, you can literally see like how much time everything took right? And for example, for me, that was very useful to figure out, should I compress my data or not, right? Here you can actually go into the compress and decompress of a file function to figure out how much time of your compute it's taking, which in other parallelization schemes, it was very hard to get to this information kind of so easily.
Yeah, that's cool. I haven't used this as much as you have, Buzz, but that makes a lot of sense. It kind of looks to me that like most, since this particular block here is read HDF5, it looks like most of the time for this pipeline at least was reading the data off disk, because the actual algorithm here is easy, right? It's just adding element-wise stuff. It should be pretty fast. But this would be a good way to check what we were saying, like if you see in this profile that most of the time is spent just sending data between workers, you've probably screwed up the parallelization scheme somehow by choosing a bad chunk size or the wrong number of workers or something like that. Mark?
Yeah, let's see. Could you, I guess what's the question? Oh, so could you describe how the structure of your HDF files relates to the size of the DASK array that you assembled? I'm assuming that each HDF file looks like it has one time point. But
Yes.
I'm wondering, is it chunked internally within the HDF file as well?
No, not in this case. Each HDF5 file contains a single data object. This is just how the data comes off of the microscope. Well, the data
Right.
actually comes off our microscope as completely raw binaries.
Right.
And then some existing sort of legacy code in the lab compresses it to an HDF5 file with just one data set that's non-chunked.
But I mean, the layout of the HDF file is not chunked.
No, I think it's just one chunk for the one big array.
So
It totally
actually
could be. And
continuously-
all of my outputs, after I do say like motion correction on our 4D data or something like that, I save everything as ZAR files. And so then I can chunk in any axis. But
Actually, wait a minute.
these are my
You-
inputs.
You said the HDF files are compressed, so they have to be chunked actually internally.
But can't you still just specify one chunk?
Well, you can load the whole data set as a whole, but in order to compress a data set within the HDF file, it has to be chunked actually. So
Yeah, I don't know.
Yeah.
I didn't design how these HDF5 files are saved, so I don't know that much about it. There could be something I'm not aware of, but I do know there's just one data set within the HDF5 file, and the metadata for that object in the HDF5 file specifies it as like the full array dimensions, but maybe there's a feature I don't know about where it's like chunked underneath that.
And so with how the workers got distributed, I wasn't sure how those mapped over the nodes or.
Yeah,
it's
it's still running. I haven't closed this cluster yet, so we can look at that. Hang on a sec. So like we built this static cluster, we ran to create the image mean, and then just to prove that it's the same as the one I made before. So we got back the same type of result as we did before. You'll have to take my word for it that it's correctly the image mean of this data set. But until I shut the cluster down, those workers are still there. So I can say, run B jobs, and I've got this set of 10 DASK workers, each one composed of 2 cores. And so for each, the other thing to point out too, you can see this clearly in the Jupyter Notebook file navigator. When I created this cluster, a folder was created in the location from which I execute or first initialize the cluster called DASK worker logs. And this is all the like LSF related output for each worker. So for each worker, there'll be a .out file and a .error file. So if something crashes or a worker exceeds its memory allocation or something, you can figure out what went wrong by looking at those logs and learn more about like how did the DASK cluster map onto B sub jobs through those.
What does the threads equal to doesn't do in this case? It basically.
Yeah, so this basically becomes the argument to -n in a B sub call. So it's saying like, let this particular B sub job, which for us we happen to know is a DASK worker, it is made of 2 CPUs. But then threads is saying, this is how many threads the scheduler is allowed to submit to this worker to run at a time. So this number should never exceed 2 times the number of CPUs for the worker, right? Because that would be the maximum number of virtual cores available to run things in parallel. But sometimes I'll set this to like 5 and this to 3 or something, because I happen to know that each thread is going to run something that's going to use a lot of RAM. So by having both of these available, I can specify like how much RAM the worker has available and how much concurrent work I'll allow each worker to actually execute. Sometimes this number's the default actually for threads, if you don't specify, is 2 times the number of CPUs. But if you allow that to be the case for a job where like each thread is doing a big thing on a big array, sometimes you'll run out of memory.
So how is DASK using threads in this case?
I really don't know. So there's this running in the local, so, this Jupyter notebook is running in another job, Jupyter, on this host, made of 8 cores. And on that, in that, that particular B-sub job, there's something running called the DASK scheduler. And that's what determine, the DASK scheduler keeps track of all of the workers that have been instantiated out on the cluster, what host they're on, what their URL is, or what their IP address is. And then it also keeps track of the task graph. What computations have you constructed that need to be run? And as soon as you say .compute, the scheduler says, okay, I've got this big task graph with a bunch of functions that need to be run, and I know all the inputs and outputs from every function to every other function, and I've got all these resources out there on the cluster, composed of workers at the following IP addresses. I'm going to now submit all that work to the cluster. And so, worker A might get a portion of the task graph, worker B might get another portion of the task graph, and so on. And so I think that what's happening is that Python process, that scheduler Python process, is submitting to threads on the workers and saying, thread A on worker A is going to execute this node on the task graph. Thread B on worker A is going to execute this part of the task graph.
Okay, I think I get it. Basically, I'm assuming that DASK is doing something multi-threaded behind the scenes in its native code, and that's and there's no it can basically run in no-kill mode in that case. Is that?
Yeah, there are options for some of the functions in DASK for turning GIL on and off, or turning GIL off. But DASK, is parallelization at multiple levels in a hierarchy. You can obviously parallel at the level of threads. You can parallel at the level of CPUs. You can parallel at the level of workers. So there's, and so for example, there's a lot of things on Stack Overflow, people who run into problems trying to combine Numba and DASK, because Numba might want to, in the JIT compiler, say, oh, I've got this many threads, and I'm going to lock those in place for my compiled for loop. And then DASK says, oh, wait, I was trying to parallelize over those threads. And so I think as soon you have to choose based on your problem what the right level of parallelization is. Like parallelizing a for loop, like what Ben is doing in Julia, you would just do it over threads on the, you've got 4 CPU cores, you would run 8 threads in parallel, right? But if each job you want to parallelize over is like an image registration algorithm or a big thing that's going to take 45 minutes and run on 25 gigabytes of data, a thread is not really a appropriately sized object for doing that. You want that individual job itself to have 32 threads available, right? So I think DASK can be tricky in choosing how to parallelize your job. And there are multiple ways of doing it. I've only really used DASK at the high levels of that hierarchy, like parallelizing over workers and CPU cores, not at the lower level of multi-threading. But most of the stuff I'm running anyway is like NumPy code, which is all multi-threaded at the level of threads anyway.
So just to note, one of the things that that Greg's package does that's really nice is when you tell it the number of threads, it says a bunch of environmental variables to tell all the downstream compiled packages how many threads to use, so that you don't run into a case where you're giving it 1 CPU and then that NumPy array checks the system for how many threads you have, and that system says 96.
Yeah,
and so that's a pretty big gotcha that using this really avoids.
I stole that from Davis. That was where I first saw that in his DASK code, where like it sets OpenMP and numkl, what those incel libraries and stuff, and the open source multi-threaded libraries. It just says how many cores does the worker actually have, set the max threads for each one to 2 times that number. So it doesn't.
So that's something you're doing in cluster wrap, not something that DASK does.
Correct.
Right.
Correct.
Yeah.
Bill.
Yeah, I had a question about, so here the bottleneck seemed to be the reading off of disk, right?
Mhm.
And so I'm wondering that, one of the advantages, I guess, of being on the cluster is that they've got pretty good connections to whatever the shared storage is, the parallel storage.
Mhm.
And so that you can sort of run the IO in parallel. So my question is more broader than just DASK in general, but like, what are the gains from the parallelism versus the, just the ability to break up your file IO? Like, have you run this on just one machine? Are you topping out on the disk read from the cluster?
I think, yeah, the actual compute CPU work here is like really low because all I'm doing is
Mhm.
adding images together and then dividing them. It's like basic arithmetic. So this particular contrived example is totally IO bound.
You're also going to have to like transmit, the image results, right? Between the nodes.
Yep.
Yeah, like,
Yeah, it just happens to be that it's cumulatively faster to read all 21 images off disk in parallel and then do the local accumulation and then do a few sends between workers is just faster than serially reading each image. But I'm not arguing that this particular way of parallelizing this problem is the best way of doing it. But if you only consider the two options of like serially running everything and running everything in parallel, or say like
well,
each
can you
worker
run
does two.
parallel on one cluster node and see, because like a lot of this disk IO, right, can be done. You can queue the requests up, and then it does up to the max of what it can actually get from the disk. And so I'm curious about like what's the real bottleneck here in terms of what are you getting in terms of parallel compute nodes that could access the shared drive all independently versus if you just run the getting all the images in parallel on a single machine that might actually have the effective bandwidth.
I really have no idea.
Because in the latter case, it might actually be faster because at least in that case, all of the images would be on one cluster node.
Yeah. Well, I mean,
so
I
that
have done that. So like before using DASK, I still had to take these image means sometimes because so for these experiments, they'll take, they'll collect 20,000 time points, and then we'll do an anatomical reference. We'll collect like 12 time points at much higher spatial resolution. And I want one anatomical reference, so I have to take this mean over like 12 time points. And I pretty much always work on the cluster, never on my workstation or anything like that. So I have just in a Jupyter notebook without DASK written a for loop: load image, add it to an accumulator, load the next one, add it to an accumulator.
Well,
it takes a very long time.
Well, yeah, but that would be serial IO on that single compute node. So what I'm saying is that if you had done that, but more asynchronously, that you had actually done the loading in parallel, aside from DASK. But I guess DASK is a good way to just do that, even if it's on one node, right?
Yeah. So like you still would need to do some custom parallel code writing to do it that way by using like the multi-threads or multi-process libraries in Python.
Right.
And you would have to, so you'd basically be doing what DASK has done for you, but manually. Give me one single worker, my B sub, my interactive B sub job with 16 cores, and then I'm going to code it with these multi-process, multi-thread libraries. That's fine too. There's more ways than one to parallelize things. DASK is a way that makes it really convenient. And I think that other alternative is possible to do in DASK by just having one really big worker and telling it that you have as many threads as as 2 times the number of CPUs that you have. It will handle setting up all the multi-processing and things. But I haven't determined which of those things is actually faster. It could be better. You're right. This example is contrived, right? Just taking an image mean. Most of the time, what I'm actually using DASK for is running a 40-minute image registration algorithm, but on 30 different pairs of images, or a terabyte-sized image that I've broken up into a bunch of blocks, and each block is at that point it's a CPU-bound algorithm. Like the IO will take 2 minutes, and then the algorithm will take 45.
Thanks.
Yep.
Yeah, just wanted to add that really what's nice about DASK is that people like me that have already learned NumPy arrays have very little learning curve to now do out of memory operations, and then slowly optimizing how to do the loading and parallelization, which is tricky, but it's definitely not at the other edge case of like Julia, where you think about algorithms a lot. You just hope that there's reasonable defaults most of the time. And it's up to you to maybe slowly optimize, but it's just on another kind of pool of users that could now do out of memory big compute with a familiar API, and hopefully not have to worry too much about all of those important things, but kind of at least it would finish and not in 3 weeks, where
Yeah,
you
fully
know,
agree.
it's I think it's useful once you cannot do this on a single workstation. That's when you should start looking at DASK.
Yeah, and most of the time, I think a DASK workflow is really designed around a custom experiment where, like, I'm one of the only people in the world who's collecting this type of data. So it's not like you're writing something that's going to be, needs to be hyper optimized for a production environment where lots of different users will be submitting different data sets to it. It's more like, I need to process my 20 terabytes of data in a reasonable amount of time. So I wrote this data, and maybe there's a way to get an extra 20% of performance out of it, but it would take an extra 100 hours of my time to learn the right way to write it. But you're only doing this, a few times on your own data.